All right, so last video, I got my 4 triangles working. I've tidied up my little arrays here, where I've got X, Y, RGB 4 times. And right now, I'm not doing anything with them. But what if I wanted to animate them? That's the next question, is how to make them like wiggle. For now, I guess we'll just have them go woo, 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 up and down. We'll use like a sine wave to make them wiggle over time. So you may have seen it already when I started the video, but this is basically what our buffer looks like right now. I took some time and I drew them out. We've got our A position is set to 2 floats, offset 0, stride 20 bytes. That's offset 0, 2 floats, 20 byte stride. And then we've got offset 8 bytes, stride 20 bytes again, and that's 3 floats. So that's what defines our vertex attributes right now. And we just, if we needed to get to this one, well, that's vertex number 1, 2, 3, 4, 5, 6, 7, 8. So if the graphics card wanted to draw vertex 8, when I tell it to draw however many that is, 12, then that's how it would do that. It's just multiplying these. So hopefully that's still clear in your minds. The question is, how do you animate your triangles to wiggle up and down? Right now, with what we know, really the only way we know how to do that would be to basically every frame, take our y's and come in here and go, okay, I'm going to send you a new buffer graphics card with some y prime, and then go through, take all of our y's that they were before, and move them, and then send a whole new buffer with new data and call draw again, and then we would get new triangles that were in different spots. But hopefully, the effort I went through to draw this out, it makes it immediately clear why that's a bad idea, because there's a lot of y's here, and this is for 4 triangles. Imagine, a modern fighting game character who's made of like 8 million polygons. All of a sudden, having his arm do this is, if his arm was perfectly round like that, there's a lot of triangles in there. That's a whole lot of data to send to the graphics card just to move it up a little bit. We have a solution for this. So good Lord, these pens. Like I mentioned earlier, the drawing I made earlier, I want red for this, was that we have our little boxes again. Our vertex shader and our fragment shader takes arbitrary data in, spits out a GL position, so that's where our vertex goes, and then it spits out other data to go to the fragment shader, and then the fragment shader spits out some color like orange. So that's the way I've described it so far. We've got our vertex shader and our fragment shader. Now what if I told you that there's a way for me to figure out how to draw, there's a way for me to draw even more arrows on this whiteboard. And that is that there's this thing called uniforms. What uniforms are a way to basically provide data to these 2 shaders that are not specific to any one fragment or to any one vertex. I'm gesturing with my hands, but I'm like kneeling on the ground here. So any one fragment or any one vertex. And that they're called uniforms. So they're basically kind of like, kind of sinful to say this, but they're basically like global variables for our intents and purposes right now. Or for the purposes of these little C programs, you can think of them kind of like global variables. So when we call draw arrays and this gets run and that triggers these to get run a bunch, say for example, we wanted all of our triangles to move up a little bit. Well, what we can do is we can say, hey, vertex shader, you also take as input some uniform called, like, I don't know, U offset. U offset. And that's another input you have. But this one is, for the purposes of this, for the purposes of this draw call, this is constant. Oh, my knees are cracking. And what that lets us do is it lets us draw, in this case 12, or we could draw like 600,000 vertices and have this not change. And that's really powerful because we can pass these kind of from the CPU, once at the start of a frame, and then draw all of our triangles, which might be 4, it might be 1,000,000. And what's even better is that UOffset, if it wants to, can also be read by the fragment shader. So, and I think I actually don't know where the name uniform comes from. I think it might be uniform because it's given to all vertices over the frame, or because it's given to all shaders. I don't know why it's called uniforms. But this is how we animate things. And in the future, we spent a lot of time talking about vertex attributes, but most of the work you do with your shaders, most of the dynamic stuff you do with your shaders is almost always going to be uniforms. And again, the reason for that is, say you wanted to do lighting, to your objects. Usually, say you had a sphere. We're working with triangles here, so doing a sphere, it requires a lot of vertices. But to do lighting, if you have one light in your scene, you need to know okay, where's the light? How bright is it? What color is the light? Where is it pointing? You do 4 or 5 little things to do lighting. If you wanted to add 4 or 5 numbers, which might all be vec4s or vec3s, that's 4 or 5 times 4 or 5 times what? 3, 30 floats times 4 bytes each, per vertex. That's a ton of extra data to throw in as vertex attributes. Instead, what you can do is represent your lights as an object in your code, like a class, a struct, or even just some numbers. And then before you run the frame, you say, okay, well, I've got, light, brightness, light bright, and light color. And now all of my vertices can get the same light brightness and light color without me having to massively expand my buffer. And also it means, for the purposes of our triangles, when we have really little numbers, it's still good because it means that we don't have to send more data every frame. Because this is, I think it comes up in an assignment question at some point. Sending data, even though this is not a lot of bytes, something I'm not going to do more mental math in my head. I've embarrassed myself enough already. Even though it's not that many bytes, sending stuff to the graphics card means that the two have to communicate. And so there's a lot of slowdown there because the CPU has to say, hey, graphics card, I want to send you something. Then it has to wait for the graphics card to stop what it's doing and be ready and whatever. So kind of rambly, but I hope that mostly makes sense. Getting thumbs up from my audience here. So let's do this in code, not with lights. We're going to do this with our writing sideways again with our offset. So how long have I been going? 10 minutes. I got this. We'll do this in code in this video. Let me pop a squat here and flip over. Whoops, not that one. Control-Alt-1. There we go. So back in here, first things first, like I said, we're going to define more inputs to our vertex and fragment shaders. We're going to do that in our shaders, obviously. So you wouldn't guess it, uniform. And I said we're going to take an offset. In this case, we're just going to take a 2-dimensional offset, and it's going to be called UOffset. And that's that. Next step, obviously, what we were doing before is we're telling, hey, OpenGL, wherever you put the vertex, that's just whatever you got in. We're not going to do any processing. But now, what we actually get in is a vec4. Excuse me. Where I'm actually going to change that to a vec2, which shouldn't break anything. Actually, it'll break something a little bit. It shouldn't break any of our JavaScript code. I'm going to change that to a vec2 because we only really are getting an x and a y. And just when I assign it to GL position, I'm going to make a new vec4 out of a position, a 0, and a 1. And that will make it work again. So my x and y are here, and my 0 on the z, so not farther or closer to the camera, and a w is 1. W is called a homogeneous coordinate, or homogeneous coordinate, however you want to pronounce it. I don't know which one is correct in this context. If you're curious about this little one here, ask Sri in lecture, bug him. Ooh, those are nice pretty colors. Beauty of using random numbers. But now what I can do is not just use a position, maybe I'll make a new thing here. Vec2 shifted position is our two-dimensional a position plus our two-dimensional offset position. And I can pass that in here. And there we go. We have successfully moved our triangles by the default value of 0. How exciting. In order to actually pass something here, we come in here. Much like attribute locations and buffers, actually. I've been drawing, I drew this one and this two, and this one. Uniforms, let me make this not sideways here. Uniforms, oh my goodness, I can't spell. That was stupid. U offset. This variable exists somewhere in memory, just like these variables. So the graphics card put an ID to it. So probably number 1. I think it might start. These might all start at 0. I don't know. Probably number 1, probably 0, something like that. But we don't know where the graphics card put specifically U offset. So we have to query for it. And I mentioned at the beginning, I haven't got to it yet, but I mentioned at the beginning that you can actually set these numbers manually and tell it that a position is always 1. You can't do that with uniforms. You always have to ask the graphics card where that is. So there are some cases where you have later, like I said, like each light you might need like 4 things. Oh god, I really got blue on my finger. Each light might need like 4 things. If you have like 12 lights, you might need 12 times 4 uniforms, and so you have a whole bunch of get at uniform location, get uniform location, get uniform location. So that can be kind of a pain in the butt, but you would just, put that in a function or call it in a loop or something, and you'll be fine. Anyway, getting a little off track. To be able to access that uniform, we need to say, we'll do it after this. So there's our buffer. Let's separate this out a little bit. So const, what's it called? U offset. And I guess I'll just call it U offset. It's kind of like, it's the U offset location, but I'll just call it U offset. Get uniform location. That's the nice thing about using VS Code is that even if you can't spell like me, it'll still figure it out for you. There we go, get uniform location. It needs a program and the name. U offset, and now I can check and see what I got. Nope, check and see what I got. And there we go. So it's kind of represented as this like empty object, but I have received some, in my case I've drawn it like a 1, but in the case of JavaScript, I got some abstract identifier for that object. So that's good. I got my little uniform, and now I basically want to pass in some value for that uniform, which I can do just by literally doing gl.uniform, and you'll see there's a whole bunch of these functions. There's basically just like, aside from like block binding, that's for like more complicated stuff, basically you have one function for every type of data you may have. And then there's, so 1f means I want to send, to whatever location I'm going to give you, so uniform 1f, 1f location and a number. This says I'm going to give you one float. 1fv says I'm going to give you an array of 1 floats, which sounds kind of stupid, but that would be if you had like an array of floats as a uniform, like a uniform, like literally uniform float 32 nums or something like that. If you wanted to give a bunch of numbers, that's when you would use 1fv, if you wanted to set a bunch of single floats as arrays. But then, in our case, we have a vec2. So we're going to use uniform 2fv. Because if you think about it, a vec2 is basically an array of, this vec2 is basically an array of 2 floats. So 2fv to u offset, and I need to give it says float 32 list. But I believe that I can just do numbers in this case. Here, in buffer data, I had to kind of convert it to like raw binary first, but offsets are, uniforms are a little nicer. So if I do, x of 0.1 and y of negative 0.2, that should budge them down. There we go. You can see that? How nice that it was. Nice and easy. Ta-da! Now they're moving. In order to animate this, I'm going to need to do this like once per frame, and you know, with some different number once per frame. So to do that, I'm going to grab this u offset. I'm going to move it out of my init function and make it a global variable, which then I can't use const because I need to redeclare it. And then I'm also going to do, I'll go over this in a separate video, my little editor hacks, my little VS Code tips and tricks video. You can tell VS Code what type something is going to be. Uniform location. To give yourself a little bit better IntelliSense, like code autocomplete stuff. Because this function, you'll notice, expects to receive a WebGL uniform location. So that's just why I did that. Now I can do u offset equals that. There we go. But now, notably, I can use it in my draw function. So after I clear the screen, but before I call draw arrays, I'm going to pass some value in here. And what happens, you know, off screen I added this little request animation frame. This just tells the browser to call this function once per frame. And that way we don't have to worry about, you know, scary things like refresh rate and, yeah, refresh rate, vsync. So this little call is going to give us a timestamp, which I'm going to default to 0 for the first time we call it. Now what I can do is, why don't I just, you know, add timestamp, I don't know, mod 1.0. Timestamp mod 1.0. And I don't remember what the precedence is on modulus, so we'll do that. Wah! So okay, we've animated our triangles. Maybe I need an epilepsy warning. Let's do like timestamp divided by 100, because timestamp ticks up in milliseconds, so maybe I don't need it to go that fast. There we go. Look at that. It's really janky, but we have our first animation. Oopsies. What might be a little bit nicer is doing, if you remember your time in math class, math.sine. I guess usually you use cos for x, or it doesn't really matter, but math.sine. I don't really need these here either. So these functions, if you remember, timestamp, and I don't really need them going radians that quickly. So again, I'll divide by 1,000. Yeah, so that means every second that goes past, they will move by some, you'll see. Ta-da! Look at that. So now they're spinning. And if I move just the y, there we go. There's the uppy downy that I wanted. And I can make them go a little faster, maybe like 500. So now every half a second, they'll do 1 radian of sines arc. You know, if you need a little refresher, you know, every half second they'll do, so pi over 2, you know, wherever 1 is, whoop. So every 1 second, the y coordinate, after 1 second has passed, the y coordinate will be pushed up by 0.841. And 2 seconds, it'll be pushed up by, again, 0.841. So as time does this, the y coordinate will do that. So a little quick refresher on sine, and cos is exactly the same, but starting at a different point. Hopefully we don't need refreshers on sine and cos, but just in case, there you go. So yeah, we have successfully animated our triangles. How long have I been rambling for? Let's see. 20 minutes. Oh, God. In the next video, I'll cover animating them differently from each other, because right now they all use the same uniform, and I call draw arrays 12, and I just draw them all with the same uniform.